Yesterday we have seen what is an analog control system and its components, how a digital control system differs from this analog control system. We have seen the difference between digital signal and discrete time signal uh, and analog signal. This is the analog signal. This discretized signal, digital signal is a code is used to represent each value, that is called digital signal. We have seen the difference between the two. The purpose of sampler we have seen, and similarly we have seen the purpose of hold element. This is to convert from discrete time signal to continuous time signal. This is about DAC, and this is about ADC. The ADC we will sample the signal, a particular sampling rate. The sampled value will be held to generate continuous signal here in the DAC. Sampling period we have seen. If sampling period is large, then it's very difficult to reproduce the original signal. It will not reflect the characteristics of original signal. For that, we have seen Shannon sampling theorem. The frequency of sampling must be at least twice the maximum frequency in that signal. So if sampling is more, we'll get the exact signal. We'll get here we are getting the signal back. It is both are identical. If you reconstruct the signal from this sample, you'll get the same. But here it is not so. If you reconstruct the signal, because the sampling is sampling period is very large, less frequency, large sampling period. That's why it does not replicate the original signal if you reconstruct from this. Here again, you see that if sampling period is very large, if you sample, then we can fit many signal with that. That's why it will not reflect the true signal when you reconstruct from that sampling period. Again, another example. Here it is sampled at here, here, and here, here. If you reconstruct, you will get this signal. There is no correlation between these two signals. That's why sampling period plays very important role in discrete time signal. Then how to select sampling period for process control? We are going to use this digital environment in process control applications, and that how to select the sampling period for that. It may be 0.1 times time constant. 0.1 times time constant. Suppose 5 seconds, the system has 5 seconds time constant means, then it must be 0.5 second sampling period. The frequency is at least 1 by 0.5. That is 2 samples per second. The frequency is at least 2 samples per second if the time constant is 5 seconds. Or the system has a dominating dead time than time constant, whichever is dominating, either time constant or dead time. We have to see if the dead time dominates, that is 0.1 times dead time. Dead time is 5 seconds, then must be the sampling period must be 0.5. Suppose dead time is 10 seconds, time constant is 5 seconds, means the sampling period must be, which is here time constant is 5, so it is quickly varying. So if the signal quickly varying means that should be captured, therefore 0.5 we have to take. Suppose time constant is 10, dead time is 5 means, then also we have to select 0.5 based on dead time. Shannon sampling theorem says that at least twice the frequency of the signal to be sampled. The sampling frequency must be twice the, at least twice, minimum twice the signal to be sampled. So, twice the frequency of the signal to be sampled. Then we have seen what is the resolution of ADC. Resolution, the minimum value that can be sensed by that ADC resolution. The change in the analog value that can be sensed by ADC is if it is range is 0 to 5 volt and 8 bit means the minimum voltage that it can sense is 0.039 volts or 0.78%. For the same 5 volt range, it is 12 bit, then it can sense much smaller voltage, that is 0.0024 volts or 0.05%. So as number of bit increases, resolution increases. Resolution increases. That we have seen yesterday. Then multiplexer, suppose the ADC will convert its signal in 30 milliseconds, let us assume. 30 milliseconds means, suppose each process need a sampling period of 1 second means all can be converted by using single ADC. For that, the input side, there will be a multiplexer before the sampler. It is called the port 1, port 2, port 3. Like that, one of the ports will be sampled, then again next, so all will be converted within that sampling period. At the appropriate sampling period, all will be converted one by one, sequentially. DAC means it is to reproduce the original signal from sampled signal. Suppose the controller output is, in our case, the controller output will be given to DAC. If it is 0 to 100% is the controller output means, if it is 8-bit DAC means 100% will be represented by 255. The 0% represented by 0. So suppose the controller has a bias value of 50% controller output means the controller output is 127. 255 multiplied by the span multiplied by 0.5, 50%. That's why it is 127.5. That is 120 is equal to nearest integer 127. What is the analog output? If it is 127 is given for a DAC of whose span is 0 to 5, 127 multiplied by 5 divided by 255, that gives 2.49. That is 2.5 volt will be given by the DAC analog output. This is a typical digital control system. Digital control system that we have seen yesterday. If you separate this into two parts, this side all analog, this side all digital. Process always analog only. That's why anything that want to interface with the process must be an analog device. Therefore, final control element is an analog device. It will work at 3 to 15 psi. Final control element valve. So electro-pneumatic converter converts the signal here we are getting 4 to 20 milliamps into 3 to 15 psi by using this. Then similarly, this analog signal is sensed by this sensor that converts this into analog signal, say 420 milliamps. That is converted into voltage, and then it is sampled by this sampler, and the ADC converts that into digital signal. So if you see left of this line, everything is digital. That's why it is called digital control system. But process always analog only. Up to that we have seen yesterday. Today, let us see um, from this point, this slide. SCADA. SCADA means supervisory, control, and data acquisition. When the digital system is introduced, all the plants in the world are analog controllers. All are analog controllers. It's not. It's a Himalayan task to all replace all controllers by digital. And because of reliability, many issues are there. Cost, reliability, many issues are there. So the immediate requirement is this: at the control room, this all process variables has to be recorded. At the same time, from the control room, instead of going to every controller, from the control room, we can set the set point for each control. Remotely, we can set the set point. So supervisory. So it reads the process variable just to read. That's all. But the set point is it is dictating to the controller. But it cannot take other control over this controller. Only it can set the set point. That's all. So the supervisory control system is a monitoring system that supervises the overall system. That's all. So this data acquisition is to record for legal purpose as well as for anything happens to investigate any accident and all. We need the data. That's why it is mandated to record all data. That's why this data acquisition. Supervisory control is it. All control loops are controlled from this control loop, not loops. All controllers, its set points are controlled from this supervisory controller. That is possible by using SCADA. But on the other hand, DCS means distributed control system. Distributed control system. Why this name? Let us see first. In a conventional control system that we have seen in the first slide, the conventional control system, everything is cascaded. Controller is cascaded with pneumatic converter. Pneumatic converter is cascaded with the final control element. Final control element is cascaded with process. Then with the process, the measurement sensor is cascaded. Transducer is cascaded with the again the transducer is cascaded with the controller. It is they are in a the arrangement is physical arrangement is required to have a closed loop. It must be connected this way. On the other hand, in a distributed control system, you will have a smart devices. For example, I am having a smart transmitter. Smart transmitter I am having. Process is here. Process is here. Here I am having a smart transmitter that senses this process variable. This process variable is sensed by this smart transmitter, and it plays its data on the bus. This is communication bus. This is the communication bus. On that, this smart transmitter, let it be the process 101, 101, and this transmitter has a tag of 102. So the process has a tag of 101. The transmitter has a tag of 102. So it always let us assume that the sampling period is every 3 seconds. It has to sample the process output. Here output, here input to the process is here input, and here output. Output is sensed by this smart transmitter. and it places its data every 3 seconds on the communication bus. That's all. A digital data is placed on this. That's all. Its work is over. Then somewhere here, a controller with a tag number, a controller with a tag number 103, 103, it knows that this controller has to control this 101 process. That's why it knows that the smart transmitter 102 will send the process variable. That's why it reads all value but reject all values except the data transmitted by 102. That will be taken by this controller and calculate the controller output M of t. M of k is digital value calculated by this, and again it places its value on the communication bus. That's all. The controller places its controller output on the communication bus. That's all. It reads the process variable sent by 102, and again it places its data along with its tag number 103. So its data is packed along with this tag number 103. It means this data is placed by device number 103 in the bus. Then another smart final control element, smart valve is there. Smart valve is there that knows that the value for its operation will be sent by 103. It knows. So it reads all value but reject all values except the data sent by 103 will be taken by this valve. Accordingly, this valve will regulate this valve for this input to this process. This valve smart valve regulates this. Here, the purpose of sequence of closed loop connection is defeated, and because all are distributed. Suppose this communication cable is about 3 kilometers length, 3,000 meters. In that, anywhere this controller can be connected. Anywhere this, not anywhere, convenient to this process, the valve will be connected. Convenient to this process, this smart transmitter will be connected. But controller can be placed anywhere. And suppose I'm having another handheld terminal that also will get the data anywhere in this bus. So the components are distributed physically, but logically they are in closed loop. How logically they are in closed loop? The data read by this is placed in the bus, that only taken by this controller. So sequence, that only taken by this controller, and it places its output on the bus. That alone will be taken by this valve. Accordingly, it will regulate it. A closed path. If you see the sequence of data, that forms a closed path. That's why it is called distributed control system. Physically, they are distributed, but logically, they are in closed loop. By using this, you can do the data acquisition also. If it is connected to a desktop PC, then you can do the data acquisition here. From another computer connected here, from here, the operator can change the set point. He can monitor the process variable. He can change the set point. So the supervisory work also can be done by connecting a communication device, computing device to this communication bus. It can be done. So the DCS is a superset of SCADA. SCADA is not superior. DCS is the superior. DCS is superset of SCADA, all digital control system. So that's why it is called a distributed control system. Then PLC. Nowadays, PLC also subset of DCS. All PLC operations can be done by DCS, but not all DCS operations can be done by PLC. That's why PLC is also subset of DCS. DCS is the superset. The SCADA comes under DCS. It only does two purposes. One is supervising all controllers and acquiring data. That's all. But those things can be done by DCS. And PLC is some sequence of operations can be done. That also can be done by DCS. That's why PLC also subset to that DCS. So DCS is the superset, and these two are SCADA and PLC are subset. The purpose of what is the purpose of PLC? PLC also a digital. PLC also a digital controller. Programmable logic controller. The sequence of operations can be done by using this PLC. What is sequence of operation? For example, a startup process. Startup process is a sequence of operation. Suppose you want to bring the process to 50% nominal operating point, means you cannot open the valve directly 50%. If you open that large oscillation, and it won't come directly to 50%. You know that suppose a person is running 100 meters race, then he will start from zero velocity, but he cannot end at zero velocity. So he will cross that line, take some time to become rest. Like that, if you want to start a process, you cannot give directly 50% valve opening. You have to open gradually and without any overshoot. If you want to bring to 50%, means it is sequence of operations. Similarly, if you want to turn on a furnace, the furnace in NLC, Neyveli lignite, it is not coal, it is lignite. It is inferior quality of coal is called lignite. The lignite is used to burn. That pulverized lignite you cannot burn directly if the furnace temperature is less than it is burning temperature. That's why to ignite the lignite, the furnace will be started with crude oil initially. So initially it will be started with crude oil. Once the temperature rises to some level, then gradually they will feed the pulverized lignite inside the furnace, and gradually they will close the liquid, and they will once the temperature is reached, they will operate by using lignite. These are all sequence of operation, not closed loop analog control. Sequence of open this valve, close this valve, open this much, close this much. So it is like on-off control, sequence of on-off controllers required for any startup process. In that case, the PLC will be very much useful. That also can be done by DCS. Now we are again come to that sampled signal. Here we know that sampling is done by using a pulses. Mathematically, it is an impulse signal. What is the meaning of impulse signal? Impulse signal, mathematical meaning of an impulse signal means its magnitude. Its magnitude is infinity. A mathematical impulse means its magnitude is infinity, but its width is almost zero. Tends to zero. Its width is tends to zero. Its magnitude tends to infinity. But energy content in that impulse signal is constant. So the sampler can be seen as an impulse whose energy is equivalent to magnitude of the signal to be sampled. So impulse means, mathematically impulse means its magnitude is tends to infinity, and its width tends to zero. If you multiply these two as a limiting case, you will get unity. If it is not a unit impulse, then that is the sampled signal. The sampled signal, how we are getting, we are representing as a impulse of this magnitude, impulse of this magnitude, impulse of this magnitude, like that. So its energy content is equal to the magnitude of impulse signal. That way we are seeing mathematically its width is almost tends to 0, but practically it is not possible. So this is the practical impulse signal. If you take it as a pulse of rectangular pulse, and even though it is not trapezoidal, it is not rectangular, because it's not possible to spike vertically. That's why it will be trapezoidal signal. But if you assume it as a triangular signal, and if you make delta t tends to 0, then you will get impulse. This is the practical impulse pulse. This is the practical impulse pulse approximated to rectangular pulse. If you make delta t tends to 0, this is theoretical impulse. But while finding mathematical model, we are assuming this is the impulse signal whose magnitude is, whose energy content is equal to magnitude of the signal. That way we are assuming. So to develop yeah, concise mathematical description of sampled signal, the impulse of infinite magnitude. Impulse means infinite magnitude. Its duration is 0, and an area is its strength. Its area of that impulse signal is its strength or energy content, and the impulse equal to that. We are assuming that its strength is its energy content is equal to magnitude of the continuous signal at which it is sampled. Like that we are taking. Therefore, let us assume that sampling points are when suppose y of t is the signal, continuous signal. They are sampled at when n equal to 0, that is t equal to 0, t equal to 1, t equal to, like that it is sampled. Every second it is sampled means it can be written as y star n of t. N varies from 0 to n, 0 to infinity. So it is continuously sampled. This t is sampling period, nt. If it is 1 means every second it will be sampled. So at when n equal to 1, t also 1, we are assuming that sampling period is 1. When n equal to 0, y of 0, at that what is the magnitude? That is the strength of this impulse signal. So the impulse signal multiply by its strength, like that we can assume, so that the sequence can be continuously written. This del of t minus n tau means impulse signal will be represented by del of t, del of t. This is impulse signal at t equal to 0, t equal to 0. But we are sampling at when t equal to 1, t equal to 2, t equal to 3, like that we are sampling. Sampling period equal to 1, 0. Sampling period equal to 1, we are sampling at 0, then 1, then 2, and 3, etc. Like that we are sampling. So how to represent the sequence of shifted, delayed or shifted impulses? Impulse is taken here, impulse is taken here, impulse is taken here, multiplied with the magnitude of the signal. Magnitude of the signal. So multiplied with the magnitude of the signal. So del of t minus nt. Delay is nt. If n equal to 0, no delay. N equal to 1 means here. N equal to 2 means delay by 2 sampling period. Like that. So del of t minus nt means delayed delayed unit impulses or Dirac function. It may be called as Dirac function. So any discrete time signal, it is not digital signal, discrete time signal is represented by y star of nt. Y star of nt. What is the value in that point? What is the value at that point? That shows the analog value correspond to this time it represents. That is called y star. Y star. Y star means sampled value, sampled discrete time signal. So the discrete time signal can be written as y star of 0, y star of 1t, y star of 2t plus etc. So mathematically this can be represented as y of 0 del of t, y of t, sampling period is undefined. If it is 1, then it will be y of 1 you will get. Del of t minus t, t minus 1, delayed by 1 sampling period, delayed by the sampled value is at 2t, delayed by 2 sampling period, like that, etc. So this mathematically, the sampled signal can be written like this. If you put this in sum of sequence, this is a sequence, this is a series. So this can be put in a summation form. Y star of t can be written as y n t, where t is the sampling period. As n is an integer varies from 0 to k. So nt del of t minus n tau, like that it can be written. So if you take Laplace transform on both sides, what you will get? What you will get here? This is the only function, time function. All are constant. Yn of t is a sampled value. Magnitude is represented by yn t at nth instant with the sampling period t. What is the value? It is a constant. Suppose in the graph, this signal is sampled at nt, it is a constant. So this is constant. And this is only variable. So y star, and this can be written as Laplace transform of sigma n equal to 0 to infinity y n of t del of t minus nt. But this is constant, taken, it can be taken outside. This summation also can be taken outside. This alone is there. Here, this can be represented. You know that in Laplace domain, any delay is represented by e power. Delay is n tau. Therefore, delay can be represented by e power minus nts. Delay will be represented by e power minus nts. So, del of t equal to 1. Laplace transform of del of t is 1. And this delay here is represented by e power minus nts. This is constant and this is equal to 1. Therefore, this is the mathematical representation of sampled signal in S domain. So y star of S equal to sigma n equal to 0 to infinity y n tau e power minus n tau S. This is the mathematical representation of sampled signal in S domain. Discrete time signal, discrete and not digital, discrete time signal. Now, yesterday we have seen what is the difference between discrete time signal and digital signal. Here, M star are discrete time signals. Here, let us reconstruct the original signal from sample data. If you want to reconstruct, what we have to do, we have to connect all points. That's all. If you smoothly connect all points, you will get the signal, sampled signal. This is the original signal. Red looks red is the original signal. This is the original signal that is sampled. How it can be reproduced? There are two possible ways. One is called by using zero order hold. Another one is first order hold. What is zero order hold? The zero order hold is we got one value at nt equal to 0. Nt equal to 0. So this value is plotted here till you get to the next value. Next value will be available only after one sampling period. Let us assume that t equal to 1. 2 seconds, 3 seconds you will get value. At the 4th second you will get value, like that. So till you get next value, maintain the same value. Then here you got new value that is slightly higher. That's why the DAC output increases. Again, till you get the third value, maintain the same value. Then at t equal to n equal to 2, you got some increment in that. That's why it increases. Again, maintain till you get next value. Next value, same value. That's why up to 4 it is maintained. At 4 there is a decrease. then maintain till next value the same value. At 5 there is a decrease in magnitude, then maintain the same value till you get next value. If you maintain that same previous value till you get the next value, then it is called zero order hold, zero order hold circuit. By using that, we converted this digital signal, discrete signal into analog signal. So it is step like analog signal, step like analog signal. For process control, zero order hold is sufficient because the process variable is very slowly varying. That's why it is better to use zero order hold itself. On the other hand, how to represent the zero order hold mathematically? To represent that, what is m of 0? M of 0 means at this, when n equal to 0, we got m value is the constant is m of 0 multiplied by del of t. That's all. Then what is m star of t? What you got? The constant value at t, and then multiplied by del of t minus, like that, etc. So if you want to convert this into analog signal, means from t equal to 0 to t first, till first sampling instant, the same value has to be maintained. So mathematically, how it can be represented? It can be represented m of t equal to, here it is written, m of t equal to m of t equal to m of n tau. N tau equal to what? 0 in this case, equal to m of 0 from time 0 to t. Similarly, next m of 1 value is, when t equal to 1, m of 1 value will be from t to greater than equal to t and less than 2t. Similarly, when t equal to 3, from 2t to less than 3t, the same value will be maintained. So you will get step-like function. So zero order hold output can be written as m of t equal to m of nt, for n of t is lies in between t is lies in between n of t and n plus 1t. Here it is between 0 and t, here between t and 2t. The t value is between, when the t value is between 0 and t, its value is m of 0. If the t value is between t and 2t, its value is m of t. If the t value is between 2t and 3t, its value is m of 2t. The constant value is maintained till you get the next value. So whatever value you are getting at 1 will be maintained up to second. Whatever value you are getting at second will be maintained up to 3, like that. So m of t equal to m of nt for with this condition. This can be written in S domain like this. How you got this? Suppose I am getting a value. I am getting a value at 0. I am getting a value at 0, m of 0. This value m of 0 I got. M of 0 is the magnitude I got at t equal to 0. I want to write in S domain. So I can, what I can do, multiply this with the step function. You will get this value up to infinity. But it is not up to infinity. It must be up to first sampling period. So after that, if you subtract another step function, you will get this value for this. So what I can do is, this m of 0 multiplied by m of 0 multiplied by u of t. U of t is a step function, first step function. This is a step function minus. After that, after when t equal to 1, there is no step function. In that case, what I can write, u of t minus, sorry, this is u. U of t minus tau, delay by one sampling period. So this is another step function after one sampling period. If you subtract this, finally what you will get? You will get this. This is its magnitude is unity. It is multiplied by m of 0, means its magnitude becomes m of 0. So the first box you are getting, the first the rectangular part you are getting. For second, what you have to do? You have to subtract the the next step function from this step function. So when n equal to 1, it is t to 2t. So this step function starts at 2, this starts at 1. If you subtract this, you will get this rectangle value. Like that, this gives means what is u of t? If you take Laplace transform on both sides, this is m of 0 is constant. M of nt is constant. We keep away, and left hand side m of t becomes m of s. The right hand side u of t is 1 by s. 1 by s. U of t minus tau is also 1 by s, but with a delay of one sampling period. That's why e power minus st by s. U of t minus tau means delay by one sampling period. So n sampling period. Then one sampling period from the sample for which we are finding the value. So one sampling period only. T minus tau means this is also 1 by s. If you take Laplace transform, you will get 1 by s, but delay by one sampling period. That's why e power minus ts you will get st or ts. So that is here. So you can take s outside. You will get 1 minus e power minus st by s is the s domain representation of this zero order hold. On the other hand, one more hold circuit is there, that is called the first order hold circuit. Here you notice that the signal is continuously varying from say 2 volt to 3 volt. But if you see a zero order hold, it remains horizontal till next value. It remains horizontal till next value. Therefore, if you are able to draw the slope, then it will be better approximation for a fast varying signal. That is tried in this first order hold. What it will do, actually, the slope of the previous two samples will be used to construct next slope. That's all. That is the idea. That's why here it suddenly turns. But what is the slope? You notice here. I'm talking here. I'm talking about here. Here the slope is this, but the next slope is horizontal only. So to draw this, to reconstruct this part, it will use the previous slope. That's why here it peaks like this. You notice here in a first order hold circuit, when it turns flat, but it uses the previous slope. That's why it comes like this. Here the slope is less, so we'll compare with this. That's why the same slope is used. So anyhow, you'll get some better approximation than this. If you compare all the three, the dynamics is better followed except at peak values. Except at peak values, all other points, the dynamics is better. Then what is the mathematical expression for this? So here also the value at this point is m of 1. M of 1. Here the value starts at m of 0, but it doesn't end at m of 0. Here it starts at m of 0, ends at m of 0. Starts at m of 1, ends at m of 1. A constant value between two samples. But here it is not so. Starts at m of 0, but its slope depends upon the previous value. Previous value is not available. That's why you can assume it as a horizontal up to this. But if you take any two consecutive values, then you can find the slope. This is how to find the slope between 2 points. How to find the slope between 2 points. What is slope between these 2 points? Find the difference between its height. Difference between these two heights. Then divide by this. Divide by this time. You will get the slope. So here value is obtained for n tau. You have to use the slope of previous samples. So The previous two values are used, this value and one value before this also used. N tau, n minus 1 tau are used to find the slope. That the difference between two values divided by the distance between the two is sampling period. If you find that, you will get slope. Once you got slope, multiply by time, then you will get the signal. You got slope multiplied by time, but the time is delay time. Here only n equal to 0. After that, it starts here, it starts here. So delay time, that's why t minus nt. So if you write mathematically, it is m of t equal to m of n tau plus m of n tau plus slope change in magnitude with respect to time multiplied by t minus nt. The slope is written in discrete domain as m of n tau minus m of n minus 1 tau divided by t multiplied by t minus nt. So this is the slope multiply t minus nt. If you take Laplace transform, you will get like this: 1 plus s tau divided by tau upon tau multiplied by 1 minus e power minus st by s whole square, you will get if you take Laplace transform. So this is the transfer function for first order hold. Transfer function for first order hold. This is the transfer function m of n tau 1 minus e power minus st by s. 1 minus e power minus st by s is the transfer function for zero order hold. This is the output. This is the input. Output by input, you will get the transfer function. This is the transfer function for first order hold. Here, the process has continuous input and output signals. It can be described by continuous models. That's why we are representing the mathematical model of process in Laplace domain. Discrete time output, of course, also a continuous signal. AD converter receives a continuous input in time domain. That's why the y star of t also can be represented in S domain. That's why the hold elements can be represented by corresponding transfer function in S domain. Here, we are reconstructing the signal, sampled signal, by using a zero order hold and first order hold. If you use a zero order hold, if you use a zero order hold, if you use a zero order hold, the previous value will be maintained till you get the next value. Previous value will be maintained till you get next value. But on the other hand, if it is first order hold, it increases it increases at the rate of previous slope. Previous slope. This slope is equal to slope of the previous sample. This slope is equal to slope of previous sample. If it is slowly varying, means both are almost identical. Both are almost identical, and if you compare these two, the first order hold is doesn't have any overshoots. It closely follows the signal. We'll compare with zero order hold, but both are in acceptable limit. But if you, on the other hand, if it is fast varying signal, this peak is missed here, this peak is missed, this undershoot is missed here. But if you see first order hold, at every peak it has overshoot is there. It has overshoot here. It has overshoot. It is overshoot like that. So both doesn't give exact replica. To improve this, we need more sampled values. But anyhow, for process control, the zero order hold will solve the purpose. In the previous example, we have included final control elements and all. Generally, a digital control system can be represented with minimum components, simplified direct digital control system. So here it is a digital system. That's why it will accept only sampled values. So a ADC is required between process and controller. That ADC with the sampler, ADC with the sampler, always ADC will preside by a sampler. Similarly, all DAC all DAC will be followed by hold circuit. If you buy any DAC from the shop, always it holds a hold circuit, because if you without holding circuit if you use, it will give discrete time signal only. So its output will be, suppose the output is 5 volt, it will give 5 volt. Output is corresponds to 4 volt, means it will give like 4 volt. Then 4.5 it will be give like this. But we need a signal like this. To connect these two, we need a hold circuit. So always a DAC is followed by a hold circuit, and ADC always preside by a sampler. Um, sampler. This is very important. So we in a simplified DDC loop, even in some books they won't put this hold circuit also, this sampler also. They will put simply ADC, DAC, like that they will put. So this is the digital controller. If you draw a line to its left all digital, to its right all analog. How to represent a PID controller in discrete form? Um, in discrete domain, how to find yeah, error? Discrete domain at nth sampling instant, what is set point? Y set point of nt. Nth sampling instant, this is sampling period. What is the process variable at nth sampling instant, y of nt? If you find the difference between the two, it gives en of t, en of tau, it will give en tau. If you multiply this by controller gain, proportional controller gain, you will get proportional controller output. So in continuous domain, how we will write m of t equal to m of t. In time domain, continuous domain, you will write kc multiplied by e of t. We'll write for proportional only controller. For integral controller, what we will write? The integral controller we will write kc upon ti, kc upon ti, integral of e of t dt, e of t dt from minus infinity to t, minus infinity to t will put. So this is integral PI controller. This is for proportional. This is for integral in continuous domain. What is the equivalent in this discrete time signal for integrator? It is nothing but summation. Here it is integrated up to t seconds present value. Here integrated up to nth present sampled value. So k equal to 0 to infinity. Integral of error, here integral of sum of error. In discrete domain, it is sum of error, as k varies from 0 to n, multiplied by sampling period. If you integrate error, it should be sampling period. Why? Because if you integrate for example, I am having error signal like this. Error signal. This is the error signal. If you integrate from t equal to 0 to t equal to t, if you integrate that, you will get the area under the graph. You will get the area under the graph. So the integral of e of t dt means this is e of t. This is e of t you are getting. E of t. E of t in y-axis. If you integrate this from 0 to t, you will get area under the graph. So in the same way, if you take a discrete domain, if the errors are sampled at sampling periods, these are all sampled values. So what I can do is, this is sampled here, and this value will be taken. Then sampled here, this value area will be taken. Sampled and this area will be taken. How to find a sampled value? What is the area of this value multiplied by t? What is the area of this sampled value multiplied by t? Multiplied by t, sampled value multiplied by sampled value multiplied by t, sampled value multiplied by t. So you can put t outside. The sampled value is, the error is e of kt. So here also, if you do sum all the areas, you will get this area. Both are almost identical if the sampling period is very, very small. So sigma t equal to 0 to n e of kt multiplied by sampling period t. So what is the integral output? Kc by ti is there. Kc by ti multiplied by sampling period, sum of k equal to 0 to n e of kt. So if you add with that, this is continuous. In discrete, m of k equal to m of n t, m of n t equal to nt equal to e of kc multiplied by e of nt plus kc by ti multiplied by sampling period, sigma k equal to 0 to n e of kt. So all errors up to n will be added, added and multiplied by kc tau by kc t. T is the sampling period by ti. So you will get digital PID controller. PI controller will be looking like this. How to find derivative? Already we have seen what is derivative here in the first order hold circuit. Already we have seen that, that is m of nt minus m of n minus t divided by t gives a slope. Slope is nothing but d by dt. So we know the slope multiplied by kc td the will give the derivative controller output. Therefore, the PID controller output can be written as m of nt equal to kc e of nt plus kc by ti tau sigma k equal to 0 to n e of nt plus that kc multiplied by td, and that slope term from first order hold. If you write, you will get the discrete PID controller. You will get the, this is continuous PID controller. This is a discrete PID controller. This is what, this is the signal. If you integrate, you will get integral of error. This is the error waveform. If it is a sampled signal, you will get error like this. All the areas under the triangles are added together, then you will get area under the graph. Nothing but integration. Approximate value of integration you will get. Similarly, to find slope between the 2 point, derivative of 2 point, the de by dt can be approximated to this value, that is e of n tau minus this value e of n tau minus e of n minus 1 tau minus e of n minus e of n minus 1 tau divided by upon t. So this is the d by dt equivalent to d by, approximately equivalent to d by dt. By using that, we obtained the expression for PID controller. Let us stop with this. Tomorrow, let us start Z transform. Let us